Hi, in this lecture I'll show you how to use the ADXL335 analog accelerometer with your ESP32 so that your gadget knows which way it's directed, which way it's placed or situated, and you can also measure acceleration, so movement in other words. This is a very simple analog sensor. You don't need a library. You connect its its data pins for the X, Y, and Z coordinates to any three GPIOs on your ESP32 that are capable of reading analog input. And then what you get from those pins is a number that relates to the acceleration detected at that dimension. So you'll get a number that is telling you whether, for example, your gadget is facing upwards like this, or downwards like this, or if it's on its side, in which case you're going to get the different measurements, say on the X axis or the Y axis, and so on. I'm going to give you some examples of how you can use those numbers to detect which way your gadget is oriented. In terms of the wiring, the way that I've connected it is this. So, zoom out a bit. So I've got the accelerometer. As far as power is concerned, I've got VCC connected to the 3.3 volt rail, and then ground, of course, connected to ground rail. So then the three data pins, X, Y, and Z, I have those connected to GPIOs 34, and then the sensor VN, which is, just look at the map here, so sensor VN is pin 39, and then I've got Z, this sensor VP, as it is marked in this schematic, which is GPIO 36. And all of those are inputs, of course, so they perfectly match the requirements of this experiment. But you can connect them to any other of the GPIOs, as all of them can be configured as inputs. All right, so let's switch our attention to the sketch. As I said, the sketch is very simple. We don't need any external libraries. All we need to do is to read the analog input at the GPIOs that we have configured. I also have information here about the sensor and its data sheet, so you can have a look at the capabilities of this sensor. In my sketch, I define the X, Y, and Z pins for the measurements of the three coordinates. I'll be printing the output on the serial monitor, so I start the serial monitor at 9600 baud. And I've also set the bit width for the analog sensor, so that's the analog to digital converter, and I've made it 9 bits wide, so that will give me a resolution of 0 to 512, which is then used down here to make determinations about the positioning and the orientation of the gadget. I'll come back to this in a minute. If you want more accuracy for some reason, then you can just comment this one out, and then the sensor readings will be taken at the default accuracy of 12 bits. If you do that, of course, the numbers here will be different. So once we do all that, we get into the loop and we take measurements just by using the analog read function that you've seen before. Take one for the X, one for the Y, and one for the Z coordinates, and print all that out in the serial monitor. But I want to use that information to make some determinations about which way the gadget is oriented, whether it's on its side, for example. You can do all sorts of determinations like that. In my case, I just wanted to do a few simple things, like whether the gadget is sitting flat on a table like it is right now, whether it's got its front to the table, whether that means it's like this, for example, or whether it's on its back, and whether it's on its side, and I make those determinations with the if statements. So all these numbers come experimentally. So depending on which kind of orientation you want to detect, then you need to look at what comes out in the serial monitor and then construct your if statements to contain those values with a small margin of error. So let's see the gadget in action. So plug that in, there goes the USB, and then upload the sketch. Okay, and bring up the serial monitor. All right, so the leftmost column is the X value, the middle one is the Y, and the right one is the Z value. And as you can see, based on this information, the sketch determines that the gadget is placed horizontally on the table. If I move it upwards like this, so that this side of the gadget is pointing to the table, then the information that we get from the sketch is that gadget front is to the table. Then I'll try also the sides. So this side, the gadget is on its side, and then the other side, I get the same message. Right? That's because I've set it like this in my sketch, so that if this condition or this condition is true, then the gadget is on its side. So as I said, these numbers that I've included in the segments of the sketch that do the determination of the position, I determine them experimentally. So for example, let's move this aside so you can take a better look. So let's say that I've got my gadget on its side like this. So you can see that the Y coordinate, the middle one, is at 274, while the rest, the other two, I don't really care about. I can ignore them. So 274 to 175, I wanted to give myself a little bit of a margin. So if the gadget is slightly on an angle, instead of just perfectly 90-degree vertical, I can still count that as gadget is on the table. So that's why I said get the analog read Y pin less than 280, or the same pin, the Y axis, larger than 270. So anything that is larger than 270 or less than 280 counts as information that determines that the gadget is on this side. And the same thing happens if I flip it over to the other side. And now I've got the Y-axis giving me a 174 value, which sits right in between 170 and 180. So with a bit of a margin of error, I can still determine that the gadget is on its side. And if you wanted to determine exactly which side, so the left side or the right side, then you would split these two conditions to the separate if statements. So there you go. That's how you can use the ADXL335 analog accelerometer with your ESP32.